Okay, good morning. So today I'm going to give you a lecture about acquisition of linguistic knowledge from Ngram. This is one of the groups which is going to happen from the next week, the summer workshop. And actually, Ken Church will host this session, but he is busy. He apologized that he couldn't come. But so I'll introduce myself. My name is Satoshi Sekine, working at NYU. I have been working on information extraction, and now these days I'm interested in acquisition of knowledge. Okay, and this is the perfect topic. So I joined the summer workshop and working from next week. And today I'll give this lecture, the first lecture in the morning, and then in the afternoon, I will give the class project, which is closely related to this talk, so better to listen. And I will introduce the task at the end of this morning session so that you can get the idea of what you're going to do this afternoon. Okay? Okay, so why we are interested in acquisition of lexical knowledge? Okay, this is actually a newspaper from New York Times 3 weeks ago. So top official is fatally shot in North Caucasus. Highest ranking law enforcement official, blah, blah, blah. Okay. So one of the NLP tasks is try to understand this newspaper. What do you mean by understand? That's a very good question. We don't know the answer, actually. But my definition of understanding this document, or any document, is try to find out all the entities in the document and find out the relationship between these entities. Okay? In this document, for example, there are many people. Okay? These are the people in this document. Not just named entity. Maybe you heard about named entity in the lecture before. But yes, these are named entities. Magmet, Tagirov. This is name, but that's not enough. We have to understand official is a person, and gunman is a person, or they are the person, etc. And in order to understand this, you have to know that official can be a person, or deputy is a person. But still, it's not easy. Official can be anything. Official can be an adverb, etc. Only in this context, official is a person, right? In order to do so, we have to know what official can be in different contexts. And furthermore, the difficulty is like this. Okay, there are many people in this document, but these orange are referring to this person, and the other color, they and their, these are the same person, etc. And also, so here, clashes between armed militant and authorities. And this gunman is related to armed militant, and this person is authority. In order to understand this, we have to have knowledge that, okay, gunman can be a militant, etc. So these kind of things. In order to understand these kind of things, you have to have knowledge. That's something we want to get. And this is only the beginning. This is about entities. Now we want to understand relation, events, etc. So this is very deep problem. Okay. So this is motivation. So lexical knowledge is essential for semantic analysis. We have to have knowledge which is not explicit in the sentence or words. And we have to create it in advance. We cannot induce this knowledge from this document only. We have to know it. And semantic knowledge is huge, so you cannot really create by hand. But now, luckily, we have huge corpus. So we want to extract this knowledge from the corpus semi-automatically or automatically. Otherwise, we have to create it by hand. Okay. There are projects which try to do this by hand, like WordNet or Psych or other open knowledge doing by hand, but the coverage is still the problem. So I'm going to talk about knowledge acquisition. Okay, this is outline of this talk, today's talk. So I will explain background, and I will show you some example of lexical knowledge, what kind of lexical knowledge we want. Then I will introduce 4 different techniques, general techniques. Okay, and then, so in order to extract these knowledge, I create some tool. There are tool, Ngram search engine. So I will introduce you this tool. Then I will explain the task, afternoon project task. And you can go to this site. This slide is available on this site, and also it has all the information about today's afternoon project, etc. So you may want to note. Okay. Okay. So 2 more slides about background. So you may have heard a lot about the machine learning last week or this week. Okay, machine learning is very powerful. It has been very powerful tool for the last decade, and they improved POS tagger, NE tagger, parser, and the technology improved from HMM, decision tree, decision list, max entropy, maximum entropy, support vector machine, and conditional random field, etc. But these tasks, so POS tagger or NE tagger, are the tasks which can be translated into labeling problem with handful classes. So POS tagger is trying to label 1 of 25 classes. So that can be done by machine learning. Machine learning can say yes or no, and you can create 26 machine learning components, then they find one of the part of speech tagger. However, lexical knowledge is not like that. Okay, there's a limitation because the lexical knowledge is huge. You have to classify into enormous number of classes if we could enumerate. I don't know if we can enumerate it or not. And limitation of training data too. We cannot really create training data which has all semantics annotated. Okay. And it is lexical dependent problem, so very sparse. You have a huge space of explosion to explore. So that's not good for machine learning, supervised machine learning. And this is quote from somebody's paper that hence it is reasonable to believe that it is inherent rather than accidental that those semantic tasks are irreconcilable with supervised machine learning method. Okay. So I believe so too. So what we have to do is we want to acquire lexical knowledge from large corpus, semi or unsupervised manner. That's what I'm going to talk about. Okay, these are the background. So I'll show you some example of knowledge we want to know, we want to extract. First one is named entity. Okay. Usual named entity is just 7 kinds, people, location, organization, 7 or 8 kinds. People, location, organization, facility, time, etc. But in the world, that's not enough. You may have to have a product name, event name, award name, occupation name, etc. And there are, for example, I create 200 kinds of named entity list knowledge. Maybe it's not enough too. But then it's very hard to do the machine learning program to annotate these 200 categories. So we have to find some dictionary or some other method to do this named entity recognition. Okay, and also there are once you go to product name, anything can be product name. Like, I cannot believe it's not better. That's very hard. No, this is just a sentence. Or event name, there are many events in the world. Okay, unless you are the residents of Scotland or Wales, you may not know this Cardiff single word competition. Well, maybe, I don't know. I didn't know this. I don't know about music so much. So, or also there are problems like ambiguity. Toyota can refer to person, company, city, and also products or awards, etc. So we have to solve this kind of problem. Okay, and coreference is also another difficult problem. So we already saw that highest ranking law enforcement official is Interior Minister is a highest ranking law enforcement official. Right? So how we have to understand this? Well, that's a big question. Okay, and name areas. This is an interesting one. Japan can refer, or Tokyo can be refer Japan in newspaper. In newspaper, sometimes it says Tokyo announced yesterday. That means Japanese government announced yesterday. So this is different kinds of name areas. Or spelling variations. This person. This is regular newspaper. I found 4 different spelling for this person. Syrian Prime Minister. Okay. We have to understand this. These can be a same person, right? And we want to know sports attribute of name. For example, if you are interested in Yankees, you want to know who is playing for Yankees, which league are they are playing, or team color or mascot or something else. Right? These are knowledge. Okay. These are kind of entity knowledge, and this is relation knowledge or event knowledge. For example, person was ambushed. There's a sentence like this in newspaper. And most of the time, I look at these examples, and most of the time, this means this person was killed, not just ambushed. The conclusion is killed. So this is inference. If people are ambushed, people are mentioned as ambushed in a newspaper of war situation, that means this person is killed, most likely. Okay. But for example, when you look at WordNet, we cannot find this information. Ambushed is under the category of weight. That's natural. But so we cannot make a conclusion that a person may be killed. And another thing is paraphrase. Okay. Person gave his life to war. If this is a normal expression, I can even understand this. This means person was killed at war. But when you look at the WordNet, I cannot find this. Okay. This is very rare expression. Okay. And another thing, so we want to handle word sense disambiguation. So language is ambiguous. Attacked can mean different things. Okay, people can attack people, but if politician attack politician, it usually means verbal attack. Politician never, unlikely, punch other politician. So this is more like verbal attack. Or other situation, it is really physical attack. So we have to disambiguate these two in order to understand, okay, if there are many physical attacks. If you are interested in gathering information about physical attack, you have to do this. And also, word sense disambiguation can be done by domain. Well, that's domain as well, but it's more like, okay, he hit has a different senses as well. In the baseball, it hit a ball, but he hits a victim in an attack event. So this is domain can find the solution for word-sensitive disambiguation as well as the context. So these are word-sensitive disambiguation problems. Okay, so these are the knowledge, and I'm not going to directly address one of these problems, but there have been several technologies to solve these problems. These are very general technologies. Okay, distributional similarity, lexical syntactic pattern, rewrite and verify, and bootstrapping. And this afternoon's task is to implement this bootstrapping. Okay, and this is based on distributional similarity and lexical syntactic pattern. So this is slightly different. These four are very popular methods. Okay. So first one is distribution similarity. This is based on a very famous hypothesis, 1985, or this is actually back to 1964, very old time. Linguists said, words that occurred in the same context tend to be similar. Okay, example. So if you have a present, someone said yesterday, something said yesterday, and this something part are similar. Okay, so words that occurred in the same context tend to be similar. That's obvious. Okay, and actually I can show you a demo, but somehow it didn't work. So I can show you the demo here. So say it. This is a demo. This is a system which search sequence of words up to 6 words in Wikipedia very quickly. It can have any wildcard in it. Okay, so this is good tool for the knowledge discovery, which actually I will explain later, and you're going to use this afternoon. Okay, and you can search like president, someone said. Oops. Oh, it's so slow. No. Sorry. It prints a sentence which includes that pattern. President. Someone said. Wow. You got lots of name about president. It's up to 1,000. Okay, something like that. So these are found in Wikipedia, or I don't know. President. Someone in. Okay, these are present name as well. That's neat. That's cute. So you can have lots of instance in some class, right? And other interesting example is dangerous. This is some information I get from they can't get other colleague of mine get from web. What is danger? If you search died in something accident, maybe this is a source of danger.
Excuse me?
Oh.
Can you make this bigger?
Oh, sorry. Okay, yeah, of course.
Thank you.
Thank you. Okay, so we can see like 710 times skydiving. Well, people can die by skydiving, or elevator accident, surfing accident, skateboarding, camping, gardening, ice skating, knitting, blocking. People can die in blocking accident. I don't know, but that's something we can find. Okay, so these are simple distribution similarity. So you can find some filters of pattern. That's some set of class of words. But that's not enough. Okay, so this is something I did at Microsoft. I visited Microsoft for several months, and they let me use query log. Okay, query log has a lots of information. That's very interesting resource. Okay, and we can do distribution similarity. So they gave me a 6 months of query log, which has 1.5 billion. It's not all. It's filtered by some method. I don't know, but they give me something like bathroom showers, pictures, Miss Mundo, etc. Okay, so this is what they gave me. And I said that I have been creating named entities, 200 naming entity category, for example. One of the categories is award. In my dictionary, I have 700 awards. 100 great baritones, Abel Prize, or I don't know, Academy Awards, etc. Okay. And yeah, we want to match this, right? Then, for example, from the query log, query like Academy Award winner, we know that, okay, some award name winner is a context for award. And we can do a lot of things because we have a big data. And so award name and context can map into a matrix. Okay? This is award name, Oscar, MVP, Grammy Award, Academy Award. And these are the contexts. For example, something winners, something pictures, something photos, something history, something winner, something award, something nominee. These are typical contexts people ask about awards. At least awards that I have in my dictionary. And this number is frequency. So Grammy pictures appears 64 times. Or MVP photos appears 8 times in the query of 6 months. Okay, this matrix. Yeah, this is big. Okay, this side is really big. This side is 700. This side is, I don't know, I don't remember, 100,000 or something. Okay, so this is good information. And what I have been explaining was, okay, you can take one context and see this column, right? This side is column. Then you can find similar one. That's basic idea of distributional similarity. But you can, once you have lots of context, you can use this. Right? And okay, then what I want to do is when you look at these contexts, some of the context is not really award context. Pictures actually appear with many other named entity categories. So first thing is, I want to get the important context for award category. Okay. Maybe winner is very typical for award, but picture is not, and other things as well. And next one is, okay, so I created dictionary using my student, master student. Takes maybe 3 months to create dictionary, but he has some mistake. Somehow he found makeup is one of the award category. That's a little bit strange, but when I investigate why this is there, then I understand that this came from a subcategory of academic award as makeup award and short film award, something like that. So he just, I don't know, cut and paste all the award name from academic award. That's why this was included. But this is obviously noise, so I want to delete this. Okay, and 700 is not enough. So we want to increase this number, populate this number, this award name. And we can do this. Okay, these 3 are tasks. The first thing is I try to find important context. And the idea is important context for this category must occur more in this category than in average. You know, that's very simple TF-IDF idea, if you know the IR. Okay, I just tried TF-IDF, it didn't work. It has some formula creation, but so basically the score, I create a score for each category, each item, number of co-occurrence of name with a co-card, number of co-card name normalized by the frequency of, so this is TF idea. Anyway. Then we found that, for example, for academic category, something syllabus, degree in something, PhD in something, master in something, diploma in something. These are found as important context. Make me happy and make Microsoft very happy too. Okay, they want to have this kind of thing. For example, if people ask about academic means physics or science or that kind, literature or that kind of thing, then you can guess that, oh, these are the things people are interested in. That's nice. For award, something winners, something nominees, something winner, or who won something, or winners of something. These are found as important context for this category. So that's good. Okay, then next task, yeah. Then we can weight, right? Winners is important. Picture is not very. Photo is not very. History, so maybe something like that. Then we want to find makeup. Is not really interesting category. Makeup is not really award category. That's obvious because the winner, the makeup winner, never appear in the query, and so the items which doesn't co-occur with the important context may not be the award name. Right? That's the idea. So I want to delete noise. Entities which doesn't co-occur with important context are noise. And example, I found this, for example, book category. IT, porno, space, night, we. These are found not a book name. Although I found that these books exist. You go to Amazon and find IT. There's a book called IT. But usually people are not use name IT as a book name in the query. Okay. So that's good. So how people use names in the queries. Okay. And also find new entities. This is easy too. Find the words co-occur with important context, but not in the dictionary yet. Other entities. And in the award category, I found Golden Globes. Golden Globe was there, but Golden Globes was not there, something like that. Grammy Award was there, but the Grammys were not there. So we found lots of nice ones. And SAG, was not in the dictionary, but we found. American Idol is there too. That's award or not. Okay, so this is a little bit trick for the distribution similarity method. Okay, I don't know. I have 80 minutes. Okay, I can try 40 more minutes. And there's a question answering time at the end, or?
Like usually they go until 10:20, and then if you stop for questions earlier than that.
Okay. Okay, I will try, and I will cut at the end. So this is different one. Different application of distribution similarity. Okay, try to find inference law, not entities, etc. So the target is we want to find X, find a solution to Y, and X solved Y means same. Okay, and well, you can do the query search using the Ngram search engine, but you can find in this context X and Y is something like communication, find a solution to strike. Government find solution to problem, or government find solution to crisis. And X solved Y, they find similar X and Y's. Okay. Then we can estimate, we can guess that these may be similar. That's a basic idea. Oh. Okay, this is sorry, Lin and Panteo paper, and idea, and okay, he has a paper on this. I don't know. Basically, everything what is I said. So they used a large corpus, 1 giga word of news, analyzed by dependency parser. So slightly different thing is they use the dependency path, not just a sequence of words. So it's more analyze all the news and try to find the verb and between verb, subject, verb, object, and to relation. Okay, not just sequence of words, but it can express sequence of words like X find solution to Y. Okay, then finds the similarities of the links. As I said, it uses mutual information. I don't know. Anybody knows? Doesn't know mutual information? Or everybody knows? I can skip this. Okay. Then finally he found the expressions which similar to X solved Y. Y is solved by X. X find the solution to Y. X deal with Y, etc. So that's make us happy. Okay, I will then skip this. Okay, and in the results, the accuracy was measured by question answering task. So question was something like, who is the author of some book? I don't know, Harry Potter or something. Then you want to get answer. And from the question, okay, they specify this is a path. But in the text, which express the answer, may not have expression exactly like this. They may be expressed by a different way. So his task is how many the system, dot system, can find the paraphrase of this. And he evaluated out of 40 how many are correct expression for this paraphrase. Okay, he found 21 for this case, and also it was interesting that he asked people make paraphrase of this. It's very hard, and the person who was tested found 7. That's much smaller. These numbers are much smaller than this system. So that's very good. So machine can find more expression, which may not 100% accurate, but that by looking at this, you can find more expression. And intersection between these two, so 7 and 21 is only 2, so people cannot find lots of paraphrase. That's a good thing about this automatic discovery. Okay, so that's the distribution similarity technique. And next one is lexicosyntactic pattern. Okay, that is in essence similar to what I explained in distribution similarity, but the difference is use unambiguous context to identify semantic relation. So people usually, in the first experiment, people gave typical, okay?
I have a question about the previous slide.
Mm-hmm.
So in the context that you explained before when you were searching for queries, you could kind of expand the initial kind of seeding parameters of the system, so you could, you decided which contexts were important, and then infer more dictionary terms to kind of expand what you started with. Is there any way to generalize to make this technique kind of infer more relationships in some way?
Oh, I see. Compared to the Microsoft experiment and this one. Yes, you can expand. For example, you search this expression in the corpus, then you can find Shakespeare is the author of, I don't know, Hamlet. True? Okay, that you find it, and next time you can search Shakespeare and Hamlet in the corpus, you may find other expression, right? Then use this expression to find the author and the book title. So you can do this is called bootstrapping. That's exactly what I'm going to ask you to do this afternoon. That's kind of expansion. Maybe this answers you or not, but that's an interesting way to do this, to expand this. Okay. Okay, so another one is, okay, use ambiguous context. So this was invented by Marty Hurst. And the expression is something like x, y, and other c, or c such as x, y, and z. Okay? If you search this expression, you can find lots of hyponym or hyponym relation, like chair, furniture such as chair and table. Then you understand chair and table is a furniture. Okay. So the key point of this is you use an ambiguous context. Okay. So such as it's so slow. I don't know. So we can find like I don't know what is good. Newspapers such as Usima, I believe this is a newspaper name. Policies such as nationalization. Yeah, we have to search more, but okay. Entertainment such as movies. Okay, lakes such as city. Critics such as Plutarch. Something like this. Okay, you can find lots of hyponym relation like this. No, well, we can play with this a lot, but okay. And we can do this technique for other relations, like happened before. So this expression is like x and eventually y. I don't know if I can find it. And eventually. Oh, I see. Okay, this and eventually it's a little bit slow. This search engine is very good. You can specify the part of speech. So past tense verb and eventually past tense verb. I hope you can get, well, maybe this, we can get the answer soon. If there are so many candidates, it takes a long time. Maybe I will stop. Maybe it should stop. Oh, I see. Okay. Okay, let's continue, and we will come back here. Okay, so and also some expression like x caused y or x because of y, that's expressed the causal relation. Okay. And this has been studied a lot since 92. So people are using syntactic structure just like dot. Or sometimes one expression is not enough. It will include lots of errors. So use multiple evidences. So that's the next. Okay. So initial paper was like this. So such NP as NP comma star or and NP, then you apply it to this sentence. Right? Such authors as Herrick, Goldsmith, and Shakespeare, then you can find this relation. But and she found she creates 6 typical expression like this. Okay, and she evaluated 92, 8.6 megawatts is very big corpus, and there are 152 matches, and 61 out of 106 feasible relations were found in WordNet. So that's not big, but that's reasonable results. But there are problems. Okay, and for example, something and other cities. Okay, you have lots of them, and this is okay. I can see this. Hope. Oh, okay. There was not an eventually thing. So, and other cities. Okay, we found lots of cities. Right. Oh, Baltimore is there. Baltimore and other cities. So we found it too. But maybe not in this list, but cities. There are areas like this. Japan and other cities. So from this result, people understand, oh, Japan is a city? Not really. Why it happens? Japan and other cities. It came from this sentence. Okay. So, fashion event being held in Kobe, Japan, and other cities. Oh, okay, that's natural, but that's noise. You know, unless we have a very smart system, we cannot solve this. So the idea is not just relying on one type of pattern. We can use multiple patterns. Then we can delete this kind of thing. For example, like cities such as Japan may not appear. Okay. It's not there. Okay. So we can delete this. Okay. And sometimes there's a noise on this kind of pattern, but it's not appear on the other pattern. So that's a way to solve this problem. Okay. So that's the syntactic pattern. Oh, okay. Another. People try this for the relationship between verbs. Okay. They define the 5 kind of relations between verbs: similarity, strength, antonymy, enablement happened before, and they create these patterns and try to extract it. Okay. I think I have to go first. And this is formula. It's not just matching patterns. They calculate the association between the verbs, so that's it's extract only the ones which is important for this pattern. And for example, this is interesting one. So there are relationships, symmetric relation and asymmetric relation. Like similarity is symmetric, but enablement or happen before is not symmetric. Divorce happens after marriage, not here, vice versa. Okay. So they have some constraint that's okay. Divorce and then married and then divorce must occur more times than 2 divorce and then married. In this case, I don't know. But so that's some constraint there. I only have 20 minutes, so I will skip a little bit about this. Okay, I think this is only one or two slides. Okay, this is another one, rewrite and verify. This is not related to the afternoon project, but this is cute method. For example, we want to understand noun phrase structure. Brainstorm cell. Is this brainstorm cell or brainstorm cell? Okay, we want to understand this. Okay, then we will rewrite this using, for example, preposition. Okay, stem cells in the brain. If you find lots of sentences like this, okay, maybe it's a right. So brain stem cell. Oh, stem cells from brain. It's true. But if you and cells from the brain stem. If we find this kind of expression a lot, maybe it's a left side, but it didn't. So this is right bracket, the right side analysis. Or you can use corpora. Corpora is a something structure of sentence. So unmarked police car. Okay, and if you find police car was unmarked, this is left side. So unmarked police car. And if you find car was unmarked police, not likely. So this is unmarked police car. Right? So you can rewrite and search the hypothesis in the corpus, and you can verify. Oh, this is the right one. Right? So that's a technique. And this is another technique, actually done by Shane there. Right? Try to find the non-referential pronoun. Okay. The expression like make it in advance. So this it is referential. It refers something. But make it in Hollywood. This it is non-referential. It's a kind of idiom that doesn't refer to anything. And his idea is, okay, replace this it by them. Okay. If this is referential, then there must be a sentence like them. But if it's not, this may not appear in the corpus. Okay? And these are number results from my Ngram search engine. He used Google, and it's the same similar result. His number is much bigger. But so we can see that the first one is referential, and the second one isn't. Okay? He evaluated. And his slide kindly gave me the information that is available here. Okay. And finally, bootstrapping. Okay, I already mentioned a little bit about this. Okay, you start. So this is a bootstrapping. This is a technique. Start from small seed of relation or expression or whatever, like for present name. In our case, Clinton, Bush, Putin, and Chirac. Okay, and they must share something, not a policy, but share, obviously. In this context, it's same context in text. Okay, President Bra said yesterday, or President Bra in, or President comma Bra. This kind of context may share by these people. Okay, then the next thing is, these contexts may be shared by other present as well, so that we can find more present name. Okay, that's the task. That's a bootstrapping. You start from small seed, gradually increase the number of example and expressions. Okay. Okay. Oh, the same thing. Okay. Clinton, Bush, Putin. So use Ngram search engine. So yeah, there is a web interface, but it didn't work with today somehow. But this is the result. If you search Clinton, there are lots of contexts of Clinton. Yeah, Clinton appears a lot in this in the newspaper Ngram corpus, which appears about 20 million Clinton. But some of them may share with other people. Okay. Then we calculate, okay, we do this for different people and find the ones which are common for these names or which are more often than other relations. Then we will find these relations, okay, or context expressions. Then from these expressions, and use n-gram search engine. For example, of president something in, you can find Clinton, Bush, Salt, Kennedy, Nixon, Reagan, Sarah, blah, blah, blah. So this is actually very good context. Okay. And you can find more president names like this. And then, again, you use this n-gram search engine to find context. And again, so you can keep doing this. Okay. That's the task. Yeah, there are lots of problems. You will be entertained by results. Once you find something different, you start getting lots of noise. Okay, that's one of the very famous problems of this method. So you have to solve this somehow. Okay, this is almost what I said. Oops, oh, it's only here. Oh, not here. Okay, so I will show you in the later that's okay how it works with my current program. Okay, so as I said, target and context grow incrementally. User gives several seeds on each sample, then the acquired data will be used to acquire new data each time. The small number of reliable data, that's reliable. This is important. How to find reliability, how to measure the reliability is a problem you want to solve. Okay, and this is combination of distribution similarity and CLSP. Okay, similar context gives similar target gives similar context, etc. Okay, and bootstrapping is basically use two different independent clues, in this case set of present and context of present. There are many different variations. Okay, once you pick different clues, it's a different kinds of bootstrapping. For example, this is another different type of bootstrapping. So you not only finding the set of entities, so they try to find relations. Mozart 1756 birth year relation. So you give several pair of name and birth year. They find in the web. In his method, he used web, and he found some expression like this: name Mozart bracket 1756. Mozart was born in something, and use this. Generalize this expression as a context as pattern, then find more name and birth year, and do this as a circle. Okay, and he evaluated, and in case of birth year, 69% accuracy, I think. Inventor. This was also evaluated using the question answering. Well, it doesn't matter so much what's the task, but it's a good to get lots of examples. Okay, so these are the 4 general techniques. And the next one is n-gram search engine. So I have been showing this, and I want to show the web interface, but I'm lucky today. Okay, and the challenge is the task is most of these discovery methods involve searching pattern in a large corpus. Large means really large, like 2 billion words or something like that. So size is big, so it is a problem because it takes time and needs machine power. Okay. And possible solutions: 1, use commercial search engine, use Google, Yahoo, Live, etc. But that is a problem. They can let us use only 1,000 times a day or 25,000 times a day in case of Yahoo. And they give us only 1,000 results, top results, by mysterious function. We don't know. Okay, we want to have everything. Yeah, frequency 1 is very important to get unpopular names, for example. Okay. And other effort, this is nice. This was happening in Japan, that academic people get together and create search engine by themselves. So the people can use freely and however you like. It's called Tsubaki system. The similar thing is not happening in America yet, I think. And the final solution is the one I'm doing. So resource poor search engine. So the first two ones use cluster machine. They have I don't know, 6,000 machines, etc., etc. But not many academic people can afford that. I can't too. So I found solution. So somehow we have to have some limitation. So the limitation is we only need local context for the search. We don't need whole text. The text which contain 2 words apart. We only need small window. So this is called n-gram. N-gram means n sequence of n-word sequence. Sequence of n-word. Okay. So it's limited only up to 7 grams search. But it works on a single CPU, PC Linux with 4 GB memory. That's I don't know. You can buy $500. Okay, and this is a little bit secret. The index is huge. Okay, 2.7 terabyte of index is needed. However, nowadays this is like $400, so I can afford to buy this. Okay, and so I have been showing the demo, so I'm not going to show you the demo. But you can search any pattern, like anything, up to 7 words. Cannot something because of, from something to something via something. You find lots of information based on this. Okay, and also this is not just searching n-grams. It's output sentence, keyword in context, so you can do for the linguistic analysis. Okay. Oh, this is just statistics. So this is Google distributes n-gram data. Maybe many of you may know. It's a big data. They extract n-grams up to 5 from 1 terabyte of text. But they have a threshold 30. So more than 30 frequency n-gram is in this data. I create 2 indexes. One is from newspaper of 86 years amount, not from 1920. It's several newspaper in mix. Okay, the text size is 1.9 billion words. That is, I don't know, 200 times or 500 times smaller than Google. But what is good with this is I don't have to specify the threshold, or 0 threshold. And I create up to 7 n-grams. And the size, for example, size of 5 gram is about the same as Google. 1 billion 5 grams, 1 billion 5 grams, 1 billion 5 grams from Wikipedia as well. Wikipedia is about the same as 80 years of newspaper. That's interesting. So you can do, and in the machine, 3 machines in the labs room, I install the index for Wikipedia, so you can play with this. And actually, the system I showed here is working there. Okay. And the discovery tool, so not just searching the sequence of words. I want to search some more advanced way, like including part of speech. That's I already implemented somehow. Or named entities, or synonym hyphonym, specifying synonym hyphonym, or other things, combination of these. And this is one of the tasks of our project starting next week. Okay, that's what I want to do. Okay, so that's basic information. And maybe any question at this moment? Yep.
Would you like to tell us about the data structure you use to store the examples?
Oh, you can give me another 30 minutes? Yeah, I think next week in our group, I think I will explain this, so I can invite you. It's basically trie structure, but trie is very expensive in the size, so there's some technique to reduce this. Thank you. Any other questions? Okay, fine. So, so this afternoon, you are going to work on bootstrapping. And this is the page. Okay, this is morning lecture. I explain the techniques. And this is a slide I used, so you can download this. Okay, and the task is get set. Okay, it's synonym for Google sets. You know Google sets? Most likely, yeah. But did you try Clinton, Bush, Putin, and Chirac? You can expect that, so let's give you present name. I pick up this four name randomly. I didn't know that it really didn't work with Google sets. Yeah, there are one or two present name, but I was surprised. It didn't work so well. Kennedy is here, Edward, Obama, okay? But so you can easily beat Google, okay? That's not the target. This is easy, okay. Oops, okay. Why I closed? Okay, so I explained. So you start with 4 seed, and you get patterns like this. And question is, what do you define the context? In this example, I defined the context like 2 words in the previous before the entity and 1 word after, or 1 word before, 2 words after, 2 words before, 2 words after. These 3 patterns are defined as context. In my case, you can define anyway. Okay, you can change it. And how to select the reliable context? So how to score the context? That's another thing. How many contexts should we use? Okay, how to select the reliable? So then another question is, when you create a target, the same question again: how to select the reliable target? How to score the target reliability? And how many targets should we use at each iteration? In my example, I use 4. Maybe you want to use 5, 10, 20. You can try different numbers. Okay, is the algorithm depending on the nature of the set and seeds? Yes, the answer is yes. And I use the same formula for president and singers. I will show you the program later. And they are different. Okay, so how to handle these differences? Okay, can we search fast enough? Most likely. I haven't actually tried this search engine used by so many people. I hope it works, but I installed this system in 3 machines, so should be okay, hopefully. Okay, but Okay. Anyway, so this is a project structure. I'm going to create 6 teams, maybe 4 or 5 people in each team. I heard there are 30 people. So, okay, and the competition. At the end, we will evaluate the results. Okay, and there is a sample program I will show you. It's a 500 lines of power. It's lots of, I don't know, lots of reasonable amount of comments in there. So 500 is not a surprising number. And so first you will read the program for 15 minutes. Then I will explain this at the beginning of afternoon. Okay, and you have 2 hours to improve. Okay, and stop implementation at 4:30. I maybe this is a mistake. The afternoon session ends 5 o'clock, right? So stop at 4 o'clock, not 4:30. Okay. Then you report and do the evaluation. So each team reports the experiment using set of new seed, not present, not single, something else. Okay. And you will send it to me, the output. Okay, like this. So actually, this is the output of the current system. You type in 4 name, and maybe the first time it's slow. It's 20 seconds later, you will get context. Maybe 1 minute. I don't remember. Including present something comma, and this is a number based on my formula. Okay, by present something comma, etc. So these are nice, nice context, and these are the first names you find. Okay, up to 5. Okay, there are 5 names, and the context at second iteration you will find this, and this is the results. I'm sorry, I cannot display the external character well. Okay, and the third context is like this, etc. Okay, and etc. etc. Okay, so this is the output format. You just use this my program, then you will create this easily, automatically. Okay, so you're going to send that kind of output to me by email for the new seeds. Okay, then after that, I will give you new type of seed. I'm not telling you what kind of people. It must be people. Okay. Okay, I will give you 3 seeds of new category, a type of person. And it's fun part of this is you can add 2 additional words, two new words of any type to the seeds. So in total there will be 5 seeds, but 3 I will give you. 2 you can find it by yourself. You can decide by yourself. Okay, then you will run your program once using the new seed, 5 seeds, and reports the results, maybe top 50, and evaluate them. Evaluate by another system, another group, team, and find a winner. So, for example, team A should send their result to team F, and F team will evaluate the result of team A. Okay, and etc. etc. Okay. Output format is 1 name per line. We don't need the context. In this case, we just want the names. Okay, and we will check. Okay, this is present. This is not present. This is present, etc. And people report how many out of 50 are really present. That's a evaluation. Okay, I prepare 3 machines, and maybe two teams share the same machine. And you can go to this directory, and the program is there. This program is there. Okay, and I already give you some hints to improve. Okay, change the number of targets count to get at each time, or change the number of iteration. If you get 5 targets at each time, then you have to have 10 iteration. But if you get 10 names, you can do the 5 iteration, for example. Or a better formula on scoring function. And this is only names. I found several times they get non-capitalized output, and most likely capitalization feature help. Okay. And definition of context, as I said, so I'm using 2 words in before, forward, after, etc. These 3 patterns, you can change it too. Maybe not, I don't know. Exclude context, which gives, this is, okay. Maybe the detail I will explain in the afternoon. Okay. And this is explanation about the program. I will just show you the program a little bit. Do I have time? Yes. No. I have to finish by 10:20. Okay, 4 more minutes. Okay, so this is a power program, but the main part is here. This is the only main part. Okay, iteration, find context, score the context, and then score the target. Find the target and score the target. Okay, I will explain a little bit more. But you can read this, and I will explain in the afternoon.
People need to know barrel for this.
Sorry?
People need to know barrel.
Yeah, that's I don't know how many people doesn't know PAL. Oh, wow. Okay. How many people among these people do you know C? Okay, if you know C, this is easy. This is much easier. Interpret language, and the variable has to start with $sign, etc. That's a little bit tricky part, but that's it. And hash and array. So each team must have a 1 person at least who knows PAL. Okay. Okay, so that's the afternoon project. And okay, that's it. 3 minutes for question and answer. Or take a break. Any questions? Thank you.